So we're going to learn how to do nodal analysis using this example problem. Step 1 is you identify each of the nodes and label each of the nodes too. So we're going to label this node V1. This node's going to be V2. This node is V3. This node that's attached to ground can be labeled as having 0 volts. And this node connected to the source can be labeled as having 12 volts. So Brett, go ahead and do the initial equations.
Sure. Okay, so the whole point of doing nodal analysis is to find the voltage every single node in your circuit. And after Morgan identified all the nodes and a few values, we still are left with an unknown V1, an unknown V2, and an unknown V3. And to solve for those, you need to set up a system of equations using something called KCL, or Kirchhoff's current law, as that stands for. And basically what it says is that all voltage going into the node is going to be equal to all your voltage going out of the node.
Oh, current going in.
Oh boy. Okay, current. Yeah, alright. So it stems from Ohm's law, and you always put the voltage signatures on top and then divide it by the resistance. So for V1, take that node and set up for your first equation. So we have 5 amps of current going in, and then we have 3 amps of current going out. And then this is the tricky part, is when you start comparing each node voltage to each other. So how we do that is we take V1 minus V3 and divide it by the resistor that connects the 2 nodes, which in this case is a 2 ohm resistor. And you do that repeatedly for every component attached to the node. So you have V1 minus V2, and then over 8, which would be that junction right there. And then you have V1 over 4. And that V1 over 4 isn't subtracting anything because it's technically V1 minus 0, because the connecting node down here is equal to 0 volts. So we just ignore that altogether. So that's your first equation. Your second equation will be concentrating on this middle node here, because again you need one equation for each node denoting all the current going in and out of it. So we'll start off with this junction right here. So you have 0 amps of anything going in. We're going to assume that all current is leaving the node. So we assume that there is none coming in, and we're going to start with that 8 ohm junction. So you have V2 minus V1 over 8 ohms. Okay? And then you also have V3 minus V2 over 4 ohms. And then down here, again, it's attached to the 0 volt node in this junction of 2 ohms, so you ignore the 0 volts. So you can just write it as V2 over 0. Oops, my bad. Doing great. V2 over 2 ohms. There you go. 2 over 0 is non-existent. Alright, so we're gonna do V3 finally. And unlike V2, it has some current going in. So you have 3 amps of current going in. And then, so you're going to start off with every other junction and assume all the current is going out again. So we're going to start with this junction right here. Then you have V3 minus V1 2. And then down here, we have V3 minus V2 over 4. Plus, and then we have down here V3. And because we know the value of that node, we don't need to express it as an unknown quantity, well, obviously. But so you just write V3 minus 12 over 8 ohms. And that's basically the essential way to set up a system of equations using Kirchhoff's current law. Because what it's supposed to be is, you know, all the current going in, all the current out. So you have, you know, some current coming in plus, you know, current going out plus another current going out. And, you know, dot, 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 and then you go to I out to whatever, how many sources of current you have bringing current out of it. But expressing it this way is using Ohm's law, so it would be the same thing as saying, you know, instead of I out, you have, you know, the difference in voltage over your resistance, which brings back to Ohm's law, which is I equals V over R. So that's just the literature.
Okay, so now that Brett has created this confusing system of equations, we're going to simplify it down to a easier one to solve. The calculations have been made
Can you
beforehand,
not
so
hit
it's a
the
little bit
tripod?
easier.
Right now, I need to redo the whole
So-
thing.
Your first one is 16 equals 7 V1 minus V2 minus 4 V3. Your second equation is 0 equals negative V1 plus 7 V2 minus 2 V3. And your last equation is negative 36 equals 4V1 plus 2V2 minus 7V3. Oops, that's not a 3. And then we'll show you or write down what the answer should be once you solve this system of equations.
So to solve the system of equations, need to make each equation just be like V1 equals to something, and then plug that into the other equations to solve for what the different voltages are. 10 volts. V2 is equal to 4.933 volts, and V3 is equal to 12.267 volts.